And although I am a biologist and I'm in a biology session here, I'm going to mostly talk about the physics of the electromagnetic fields generated not from the body, but from a Caduceus coil, which is another experimental way to generate what I call non-classical electromagnetic fields, because I believe that bioenergy, which we've been talking about, although there is an electromagnetic component, the more exciting and interesting and anomalous effects are the non-classical nature of the energy that's emitted by these fields. Do I need this or not? No, okay, so I want to start with in the title, there's a lot of concepts in there, so I want to start with the concept of what a longitudinal field is. And in order to describe what a longitudinal electromagnetic field is, which is a non-classical form of the electromagnetic field, I have to start with the classical electromagnetic fields that don't move. Well, they do move, but they propagate differently than this button does, which doesn't work. Oh, I have to. Oh, I'm sorry. Gotcha. Okay. So here's the classic electromagnetic field, which for those 60% of the audience who are not physicists, which I just learned in this conference, looks like this. It may not look like an ordinary electromagnetic field, but you can see the electric and magnetic components which oscillate in a transverse or perpendicular direction to the direction of propagation of the field itself. And that's why they're called transverse Hertzian force fields. This is the classical definition of an electromagnetic field. And what I'm going to talk about is a different kind of field that doesn't have a transverse oscillation, but a longitudinal oscillation. So here's the physics part. I will get to the biology, promise. We're in a biology session, right? So there is some biology in here. So Maxwell's equations are complex, and I'm not really qualified to talk much about them, but I will anyway. So they are described mathematically by these mathematical entities called E, B, and H, which are mathematical vector entities. And then there's potential mathematical constructs, which are called potentials, which underlie the vectors. And in fact, an electromagnetic force field can be described in terms of its potential components as well as its vector components. And the A stands for the magnetic vector potential, and phi is the scalar electrostatic potential. I will mention that later because that's an important concept. But anyway, traditionally, the solving of Maxwell's equations are done within a certain set of confines. There's only a certain kind of algebra that's used. There's only a certain kind of operators or mathematical constructs that are allowed. There are certain boundary conditions that are used, and there are certain coordinates within those boundary conditions. So in a sense, the Maxwell's equations are limited by these conditions. And when you solve the standard Maxwell equations has lots of different forms. When you solve the classical form of the Maxwell's equations, you look for wave-like solutions. In fact, there are so many different solutions you can get when you solve these equations, but what we're interested in is wave-like solutions which describe the behavior of the classical electromagnetic fields. Now, the behavior is the properties of the fields or the propagation of the field, and physicists seem to be very obsessed with how these fields propagate and the speed that they propagate. For example, the behavior also has to do with the way that the fields interact with particles and the way that these mathematical components interact with each other, how the electric and magnetic components interact with each other. and how the fields are transformed. Mathematicians love to take these equations and then transform them, like put the equations in another set of coordinates, and then what happens to the field. So conceptually, that's the kind of things that mathematicians do in classical field theory. And what I'm now going to suggest is that there are some limitations to these classical. Oh, I don't have to look there. I can look there. Hey, no, that's cool, right? And I can sort of look at you at the same time. So there, as I said in the beginning, that Maxwell, in order to even develop these equations, Maxwell had to set certain limitations, and these are some of the quotes limitations. That force fields are considered to be uniform throughout space, when in fact there are also non-uniform electromagnetic fields. Space is considered to be a Euclidean space, which is usually modeled as a sphere or a cylinder, when in fact there are all kinds of other spaces that that now physicists consider, but Maxwell did not consider. Obviously, it makes the mathematics a little more complicated. The oscillations are assumed to be transverse, and I've actually read in some articles that the longitudinal oscillations are not allowed in Maxwell's equations. The velocity is considered to be less than or equal to the speed of light, and in fact there are fields which propagate at supraluminal speeds, faster than the speed of light. The Lorentz gauge is something I will talk about in a moment. That's kind of, for all the non-physicists, it's limited, it's an arbitrary choice of one kind of gauge, the Lorentz gauge, when in fact there are many others. And then they make all these mathematical assumptions, like they set all these variables to zero, like the magnetic charge density is set to zero. The divergence of the electric components is set to zero. That means kind of the divergence means like the expansion of the field is set to zero. And these are kind of arbitrary definitions. Why would you set that to zero when a field can expand? But it simplifies the mathematics. So Maxwell had to do some kind of limitations. And then there's the whole thing about the potential fields and the potential, the A and the phi mathematical descriptions that describe the fields. The potentials are not considered to be real. They're a mathematical construct. And then much later, Aronoff and Bohm and several other people have actually demonstrated that potentials, in fact, are real, and there are fields associated with them. According to Maxwell, the potentials are considered to be instantaneous, and they're described in terms of an arbitrary gauge function. Okay, so these are what I would call the limitations of Maxwell's equations. And then, as a result of that, the limitations. So let's look in the mathematics a little bit more detail, because the gauge, I was talking about the gauge theory before. So gauge theory is a theory based on a certain kind of group theory mathematics that I've talked about, which is Abelian in nature. It's a kind of vector algebra. It associated with each mathematical group is a field, which is called a gauge field. And the gauge kind of refers to the degrees of freedom that are given when a field is transformed into another dimension. And it's considered a bad thing. The field shouldn't change its properties when it's transformed looked at in another set of coordinates. So they always try to limit the number of degrees of freedom by a process called gauge fixing. And gauge fixing, therefore, imposes certain limitations on the fields. And that's, again, another kind of way in which the fields are limited in their properties and in their behavior. Gauge theory is, again, based on group theory, and the groups are characterized primarily in terms of their topology and their symmetry. And this is kind of all going to be important in a minute, so hang with me on the physics part for a moment. So the topology, which refers to like the shape of the space, like I was talking about before, usually a sphere, or technically it's called a manifold or a matrix, which defines the field. So, typically they consider the field as fundamental, but the topology is secondary. But in fact, some modern physicists think it's the other way around, that the topology or the shape of the field determines the characteristics and properties of the field. But the topology, in any case, the topology imposes a boundary, which is a kind of limitation on the field, but it is a way of characterizing the field, particularly in gauge theory. And even more important is the symmetry. And typically, the kind of local symmetry that was used by Maxwell and in Maxwell's equations is called the U1 group symmetry, which is a mathematical definition of unitary local symmetry. Okay, now that comes important in a moment. So it turns out, as I said earlier, that the gauge that Maxwell chose was called the Lorentz or Coulomb gauge, and there are alternatives to this kind of gauge that use non-Abelian algebra that have a different kind of symmetry, and in fact, with these other gauges, you can have symmetry breaking, which is not allowed in the classic theory. Longitudinal oscillations are allowed, so it kind of opens up the limitations that Maxwell has imposed on the definition of electromagnetic field. And these are the kind of names of the different kinds of gauges that are alternative to Lorentz gauge. There's also alternative symmetries involved. Mathematicians, love doing this kind of stuff, and they say, well, we don't have to stick to the U1 gauge. We have all kinds of gauges and all kinds of manifolds that can be used to actually define the nature and the properties of the field. I'm saying all this because these topologies or asymmetries are defined, here they are, wrong button. Well, let's go back to this. The SU gauges and SO gauges and SL gauges are defined as higher order symmetries that generate higher order fields than the classic U1 symmetry electromagnetic field. They have been called supersymmetries, and they're associated with, chiral. But anyway, the mathematics gets pretty complicated, but just to visually show you some of the alternatives to a sphere, needless to say, they get a lot more complicated, and the mathematics gets a lot more complicated. Oh dear. Okay, so when you solve these Maxwell's equations, you get different kinds of solutions. You get new, that I don't really have time to go into, but they allow, and they generate different kinds of waves. These waves have been called all kinds of things, and longitudinal waves and scalar waves, waves where the electric vector and the magnetic vector are not perpendicular, but they're parallel, and vortex fields. Here's a picture of a Beltrami field. Anyway, the point, and they have all kinds of different properties where these fields are not classical. The properties are not classical. So what we're talking about here is different experimental methods of actually generating these fields. You can generate these fields by different kinds of electronic coils. And here's the toroid, which is the classic example, because the classical electromagnetic fields are trapped inside, but potential fields are known to exist on the outside. And theoretically, this has been known for a long time, but it turns out there are lots of different kinds of geometries and different kinds of coils that have been used even in the electronics industry for various applications. But most of this has been rather theoretical, and this particular paper is a theoretical paper describing the nature of the fields that are generated from a toroid, for example. And in this particular case, the fields are mapped in terms of the two A fields, which interact with each other, which makes it a little more complicated. And here's the shapes of the fields. And this particular paper describes the nature of these fields as not being U1 symmetry, but being U2 gauge symmetry. And the properties of these fields are that they are complex, they're called self-dual, they have some unusual properties, they don't involve photons, they involve instantons, and this is the theoretical physics. Recently, as in last year, some experimental studies were finally done and published in a physics journal using these kind of fields, where they actually measured the magnetic component of the fields on the outside. You cannot measure SU2 symmetry fields using ordinary electromagnetic detectors. So all they could do is measure the U1 field, that is the ordinary field, that is emitted by these kind of coils. And they conclude that the magnetic field patterns, first of all, they don't fall off like ordinary electromagnetic fields, as in proportional to 1 over r squared. Their pattern of distribution is inconsistent with U1 fields, and they have unusual behavior, even in this case where you're only measuring the U1 classical component. So there's something strange going on when you generate fields. I don't have time for this. But using a toroid or a Caduceus coil kind of configuration. So the experiment that I did was using yet another kind of configuration where the current in this kind of a coil, a flat coil, it comes in at one end, as you can see in the far right corner, it turns around and it goes back out in the other direction so that the current is opposing, the current cancels, the magnetic force field, the vectors cancel, and you generate some kind of a potential field like described in the two papers I just described. So you have some kind of an SU2 field, non-classical field generated. The experiment involved a complex square wave that was put into the coil in the form of a modulated square wave riding on top of a sine wave. And then we actually measured, there was a residual magnetic field component that you could measure, a U1 component, but what the actual experiment was is a biological experiment where I used human lymphocytes, which are immune cells, T lymphocytes. It's kind of a standard assay. They're grown in tissue culture, and then you, they're isolated from human blood. You isolate the T lymphocytes from the other blood cells, and then you put them in a tissue culture dish. You treat them with radioactive thymidine, which it gets incorporated into the DNA. It's a standard method for measuring cell growth. You actually measure the radioactivity incorporated into the nucleus, and then you calculate the radioactive counts by the total amount of protein, and then what you get is this. So in the control situation, there is a very small amount of growth, but in the presence of the non-classical electromagnetic field generated from this kind of self-canceling, non-inductive coil, you get a relatively large stimulation in growth. When you use a standard chemical mitogen called, I'll be finished in a second, called interleukin-2, you get a similar kind of growth. And then when you combine the two, which is this, there is no enhancement, which is the same effect that Dr. Gupta got when combining energy and chemicals. So in conclusion, the fields that are generated the non-classical gauge fields of SU2 symmetry generated by this kind of a coil does in fact stimulate human lymphocytes. The magnitude of the effect is very large. It's in the order of 20-fold. In fact, there were more than one signal, and some signals work much better than others. Signal 2 was less effective. There was no additivity between a chemical and an electromagnetic field, which suggests that they work via the same mechanism of action. And the large stimulation is anomalous because in the literature, standard classical electromagnetic fields are known to stimulate lymphocytes, but not on the order of 20-fold. Typically, it's on the order of 50, 80%. So that's where the anomaly is, and that's my conclusions, and thank you very much. Ta-da! There's my information. Did it? Okay. That 20 minutes is tough.
We have, 20 minutes is short, but let's take a couple of questions.
Yes, my name is John Reed. Glenn, your research is very fascinating because it appears that this has great applicability for enhancing the immune system, and that's one of the directions I think that medicine is going in the 21st century, like we were discussing last night.
In the panel.
But have you, were they specific T cells? Were they the T4 or T8 or what T cells were they? Because this has potentially great applicability to perhaps treatment of AIDS, since, as you know, it's the decline in the T lymphocytes that results in the AIDS problem.
And the panel, we were talking about helper cells and suppressor cells, which are the two types of T lymphocytes. In this particular preparation, I did not separate the helper and the suppressor cells. So this was a combined preparation that contained both helper cells and suppressor cells. But both of those are called T lymphocytes. So I did not separate the two different types of lymphocytes. That would be great for future research.
Hi, my name is Sean Lakshmanan, and I have a question on the Maxwell's equation.
A physicist. Okay.
So you were talking about the scalar potential. Basically, for the magnetic field, there is no charge. And therefore Maxwell included the scalar potential equivalent to that of a charge, so you put an artificial kind of a potential that appeared. So how do you correlate that with these, your SU2 to fit into that equation? So you're telling it is, if it is a non-classical, it should generate by itself. You need not have to introduce a electric unit to cancel itself and do any other thing. So it should, without any electrical interference, you should have a output.
Yeah, well, in the previous study by Barrett and the follow-up study by Froning, they compared the cancel mode and the non-cancel mode, where the current's running parallel versus anti-parallel. And I didn't have time to go into that in much detail, and I'm sorry for Yuri didn't get a chance to ask probably a very good question, but we'll talk later, Yuri. And you're right, in both the cancel and the non-cancel modes, you do generate the SU2 non-classical forms of the field. But the point that they made there is that the behavior of the fields that are generated outside of the toroid or a Caduceus coil or whatever is different in the cancel mode and the non-cancel mode. So the conclusion was that you generate SU2 fields in both situations, not necessarily because of the cancellation, but because in the case of a toroid, the fields are trapped, the classical fields are trapped in the center. The U1 symmetry fields are trapped in the center of the toroid, but the SU2 fields are free to be generated on the outside of the toroid. But I didn't use a trapping kind of geometry. I used a cancellation geometry. in order to generate the SU2 fields. So it's a little complex, but conceptually that I think is what's going on. We can talk about it more. Thank you.
Thank you very much.